All right, welcome to this explainer. Today, we're diving into the gritty, honestly deeply fascinating world of excavating dead servers to unearth a lost digital civilization. Most people just assume that when the power finally fails or the hardware physically collapses, the data just dies right along with it. But as we're about to see, the truth etched into all that silicon is far more persistent. And recovering it, well, that requires this incredible mix of forensic science and digital engineering.
Okay, picture a server room. The fans are totally seized up, the capacitors are bulging, and you catch that faint, unmistakable smell of burnt circuitry leaking from the chassis. The server is dead. Not sleeping, not hibernating. Dead. But here's the thing. To a forensic data archaeologist, that dead server isn't an empty grave. Inside that stack of rusting magnetic platters is a layered, totally readable stratigraphy. It's full of unallocated entropy just waiting to be read. There's no directory anymore, no file names, no handy index, just raw data surviving right beneath the surface chaos.
So to really grasp what we're doing here, we have to distinguish between your standard data recovery and digital salvage archaeology. Standard recovery assumes you, generally know what you're looking for, right? You have an index or at least a rough map of the territory. Salvage archaeology, on the other hand, is a blind excavation. It's the systematic recovery of unindexed, invisible, completely orphaned files from a fully failed storage medium. Whether we're looking at a huge corporate collapse, a criminal investigation, or a historical preservation project, the objective is exactly the same. We literally have to teach the dead hardware how to speak again.
Section 1. 3 Layers of Death.
So this decay doesn't just happen all at once. It hits in 3 distinct stages. First up, we have logical death. This is where the address book of the server, like the master file table, is wiped or completely corrupted. The server absolutely still has the data, but it's entirely forgotten where it put it. Descending a bit further, we hit structural death. You see this a lot in complex RAID arrays where the controller fails. You might have 5 perfectly healthy drives, but absolutely no idea which byte belongs to which file. It's a mess. Finally, we reach physical death. This is your straight-up hardware failure and bit rot, where magnetic domains physically flip and NAND cells lose their charge. The data is still there, but the physical pathway to actually access it has completely collapsed.
All right, moving on to Section 2, Rules of the Trench.
Now, down in this digital trench, the stakes are incredibly high. The very moment you power on a failing drive might actually be the absolute last time it ever spends. Because of this, we have one cardinal rule. You never, ever work on the original medium. Every single interaction with a dying drive, every spin of that platter, every electrical pulse, risks inducing further mechanical or electrical degradation. If you try to extract your files directly from the dying drive, you might just destroy the exact history you're trying to save. No way! We absolutely must secure the site first.
And to secure that site, we use a hardware write blocker. This thing acts as our absolute safeguard. It's a specialized physical bridge that sits directly between our computer and the dead drive. What it does is intercept all command signals, totally ensuring that the host computer cannot write a single microscopic bit back to the target drive. It forces this strict one-way street of information, which lets us safely extract a forensically verified clone, a sector-by-sector bitstream image that captures everything: the deleted files, the partial sectors, and all that unallocated empty space.
Once we've got that barrier up, we grab our digital shovels to actually extract the clone. We use specific software tools, programs like DD Rescue or FTK Imager, to meticulously scrape the raw magnetic states right off the medium. And we're doing this even while the drive's firmware is practically screaming for help and throwing read errors everywhere. We are literally pulling a ghost out of the machine.
Which brings us to Section 3, Sifting the Digital Dirt. Okay, so with our ghost image safely secured, we can finally put the original dead drive away and jump into Phase 2, file carving. This is where the real archaeology kicks in. It's basically the digital equivalent of sifting through massive piles of dirt just hoping to find tiny pottery shards, all without a catalog to guide you. Because that file system index is gone, we can't rely on folder names or file extensions anymore. The machine honestly has no idea what a photo or a document is. Instead, we have to scan the raw binary stream for what we call magic numbers. These are unchanging byte sequences hidden deep in the data that serve as universal structural signatures for specific file types.
To put that into perspective, every single JPEG image in the world begins with the exact same structural signature. The hex bytes FFD8FF. A PDF document? It always opens with %PDF. A zip archive will always carry PK, followed by some specific control characters.
By knowing these hidden architectural artifacts, our carving tools can sweep through millions of gigabytes, byte by agonizing byte, and completely rebuild the data based solely on these internal structural blueprints.
The precise digital brushes we use to identify those headers are carving tools like Autopsy or PhotoRec. These tools are amazing. They just ignore all the chaotic noise of the unallocated space and hunt exclusively for those magic numbers, perfectly reconstructing the files from the inside out.
And you know, the real-world power of file carving absolutely cannot be overstated. In fact, this exact technique is how investigators caught the notorious BTK serial killer. He handed a floppy disk over to the police, completely believing it was perfectly safe because he had deleted the files. But he didn't understand that deleting a file only removes the index pointer. The actual document structure and all the embedded metadata completely survive the deletion. Carving revealed the truth, basically proving that meaning and data survive long after the user thinks the structure is destroyed.
But of course, modern servers kind of complicate this carving process with fragmentation. Today, a single document might be shattered and scattered across a dozen different physical locations on a disk. To combat this, we rely on statistical entropy analysis. We mathematically analyze the randomness of the data shards. Encrypted files, for example, look like random white noise and have extremely high entropy. Plain text, on the other hand, has low entropy because of repetitive language patterns. By charting these mathematical shifts, we can algorithmically guess which of those scattered digital shards actually belong together.
Let's pause right here and raise the stakes a bit. Everything we've discussed so far works wonderfully on a single drive. But what happens when our puzzle pieces aren't just scattered on one disk, but distributed across completely different physical disks in a complex RAID array?
Section 4. Solving the RAID puzzle.
When a RAID controller dies, the array appears to our computers as completely meaningless raw data. The hardware map is just gone. Suddenly, our digital archaeologist has to drop the shovel and basically become a cryptographer. To rebuild the data, we have to manually unlock the array's hidden geometry, things like the RAID level, the stripe size, and the parity rotation. We do this by running these complex chi-square tests on the byte distributions across each individual drive. We're hunting for the exact offset where the data's entropy normalizes. By finding that mathematical sweet spot, we force the shattered array to reveal its own geometric logic, letting us weave the drives back together virtually. It's incredibly cool.
But even if we rebuild the array, we face our final, honestly most insidious enemy down in the trench: physical bit rot. This is the silent scream of dying storage. Over time, magnetic domains spontaneously flip, and NAND flash cells slowly leak their charge. A 1 silently becomes a 0. Just one single flipped bit can completely destroy a massive database or corrupt a high-resolution image, totally collapsing the pathway to our unearthing.
Fortunately, we have a serious anti-entropy arsenal. Using mathematical safety nets, stuff like finite field algebra and Reed-Solomon erasure codes, modern salvage tools can take data where up to 20% of the file is completely obliterated by bit rot and actually rebuild the missing pieces using the remaining 80%. We aren't just recovering bits here, we are actively fighting the relentless laws of physics and entropy to preserve human history.
Section 5. The illusion of the cloud.
Let's zoom out to the macro view for a moment and shatter a massive, super pervasive myth about where all this data actually lives today. We hear so much about the cloud, right? Like our data just floats up there in some ethereal, untouchable atmosphere. But the cloud is really just a carefully manufactured corporate illusion. In reality, the cloud is a sprawling, deeply physical necropolis of spinning magnetic platters and fragile silicon wafers sitting in massive warehouses. It is a strictly physical medium. And while modern solid-state drives are definitely becoming increasingly hostile terrain for recovery, mostly due to automated trim commands that electrically purge deleted data, the physical imprints of our lives still remain etched into hardware much longer than we assume.
Because of this physical reality, and as the world's digital infrastructure naturally ages, the demand for people who actually understand this stuff is skyrocketing. Mastering these forensic engineering tools, learning how to navigate unallocated space, mastering software like RStudio to rebuild RAIDs, and memorizing the hex signatures of proprietary databases. This is no longer just a niche hobby. It is quickly becoming an incredibly lucrative, high-value career path in cybersecurity, legal forensics, and historical data preservation.
So what is the ultimate takeaway from this explainer? It's a pretty profound one. Meaning survives far longer than structure. The index might vanish, the hardware might literally burn, and the systems will inevitably fail.
But the foundational truth that raw data can absolutely still be carved out of the silicon if you know exactly how to listen to the machine.
Our digital footprints are incredibly vulnerable to time, yet shockingly permanent. The map is not the territory, and the deleted file is rarely truly gone. So I'll leave you with this thought. What forgotten data is quietly waiting in your old, discarded hardware right now, just waiting for someone with the right tools to find it? Keep digging. And hey, if you want to see more deep dives into the hidden, fascinating layers of our digital world, be sure to hit that subscribe button.